Hello, everyone, and thank you for joining today's session. My name is Irina, and I'm the event planner for the Redmond Reactor Space. Before we get started, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience as well as our presenter. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. Useful links will also be shared in the chat. This session is recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. This session will run approximately 1 hour with questions throughout, and I'll now turn it over to our speaker for introductions.
Awesome. Thank you very much. Good morning, good afternoon, good evening. Hello, wherever you are in the world. And welcome to today's session where we are counting bears with the power of the Internet of Things and a little bit of AI mixed in. So if you've not joined one of my streams before, I'm Jim Bennett. I'm a regional cloud advocate at Microsoft. So it's my job to do cool live streams like this and then help tech communities, work with tech communities where I live in the Pacific Northwest of the US. So welcome to the session. Glad to have you all here. This can be a very interactive session, so feel free to jump in the chat, ask questions, get involved, and just let's have a fun conversation whilst we play with some bears and a bit of AI. Now, if you want to reach out to me after this session or you watch this on demand, I'm all over the internet at Jim Bob Bennett. Twitter, GitHub, Instagram, LinkedIn. Please feel free to connect, reach out, ask questions. Always happy to geek out on IoT with anyone. And little Andy 77, that looks like a Patrick from SpongeBob. I know SpongeBob is very cool. My daughter used to watch a little bit. I don't watch much. I think it's Patrick. So hello, wave in. Nice to see you. Glad to have you here. Now, today's session is an IoT session, and it's all part of what we call JulyOT. So all throughout July, we celebrate the Internet of Things simply because of the name JulyOT. What better month than July for celebrating JulyOT? And JulyOT is a month-long celebration of the Internet of Things where we try and bring you great IoT content for you to learn, maybe get certified in various cloud technologies, find some cool new projects to work on, and then for you to share the cool things that you're doing as well. So we're on the internet, JulyOT.dev. If you head to that site, let me just drop this in the chat for everyone. If I can do the typing thing, drop that in the chat for everyone. If you head to JulyOT.dev, brings you here. We have a whole lot of great stuff for you, from a cloud skills challenge where you can compete with other people to learn about Microsoft Cloud when it comes to the Internet of Things. We've got digital swag like social media images, stickers you can download and print yourself, desktop backgrounds and Teams backgrounds, all celebrating JulyOT. Also celebrating JulyOT, which is JulyOT in Spanish. And then we've got lists of our upcoming live streams around IoT. It's got a whole lot of great stuff coming there, a few meetups, a load of IoT resources, and most importantly, our JulyOT blog. So here pretty much every workday, the site's going to load, it's playing silly walnuts now. Pretty much every workday, we're posting new content in either English or Spanish around IoT. So we've got things like how to do closed captioning with a Raspberry Pi and cognitive services. We've got a lot of live streams around IoT for beginners, got AI on the edge with Azure Percept, .NET Nano Framework, whole lot of great stuff. And every workday, we keep putting more stuff on here, one or more posts. So head to JulyOT.dev, get involved, and then share whatever you're working on social media with a hashtag of #JulyOT. We want to see what you're working on, and we want to help share it with the world. So today's session is all about bears. So I'm a Brit, as you can tell from the devilishly good accent, but I've recently moved to the Pacific Northwest of the US. So I'm in Washington State, in Redmond, the home of Microsoft. Now, when I lived in the UK, pretty much the only thing that was scary that might jump out at me might be like the occasional hedgehog. Maybe a badger might cross my path. You know, not too scary. But here in the Pacific Northwest, we have bears and cougars and bobcats and other kind of large, scary animals. In fact, this particular bear, you may notice down the bottom of the picture here, looks a bit like a fence post. That's because this bear climbed on my fence, climbed into my apple tree, ate a load of my apples, and then disappeared through my back fence, breaking off a large part of the tree and taking down my fence. You can see the damage there as it took out my back fence. So if anyone here has ever had any bear encounters, let me know, or other interesting animal encounters. Please put it in the chat. Love to kind of hear what fun things you've experienced with wildlife. But this bear, so it's not a great picture, but I was probably only about 3 or 4 meters away, trying to zoom in, catch this bear in the trees. Kind of very scary. Took my bins out one day, and then just saw this bear about 3 or 4 meters away from me. Obviously, had to take a picture before I slowly backed away. But a little bit scary. Little Andy 77 says no bears in Sweden. No, I guess polar bears don't necessarily head that far south. I know, like with Norway, you get like islands like Svalbard where you get polar bears, but don't get any polar bears anywhere in Sweden. I guess it's a bit too far south, isn't it? They're kind of a bit further north. But yeah, not a place where we get all the different big black bears and brown bears and grizzly bears that we get here. So I thought it'd be fun, if I'm thinking about bears, to detect bears. So kind of asking the question myself of how can I detect bears? What can I do to actually see whether the bears have come into my garden, get some pictures, just be aware of the bears. Maybe not let my 9-year-old out if there's a bear in the garden. And there's a number of different ways to do this. So kind of one of the classic projects you get is a wildlife camera. So there's like a million of these. Just Google with Bing for wildlife camera, usually with Raspberry Pi. You normally end up with some kind of setup where you have a camera connected like a Raspberry Pi or similar device with a motion sensor or a distance sensor. And whenever that triggers anything, it captures the image. Or you get ones that monitor the camera feed. And if the camera feed changes because there's motion, it'll start recording. And that's quite a normal setup. And then sometimes you just go and grab the SD card out the Raspberry Pi and download the pictures. Or if you've got Wi-Fi connection, put it over the internet. And that can be a bit of fun. But the problem you've got is you can't tell the difference between different animals. You're just capturing motion. And little Andy says, we actually get brown bears in Sweden, but not around where I live. Okay. I guess, yeah, because bears do have spread kind of across the, I forgot the word from geography back in the day, but all the kind of the forestry regions that go around the top of the Northern Hemisphere. You kind of get bears around there. But what animals do you get? I'm intrigued. What kind of wildlife do you get turning up? So what I get raccoons. So this is a capture from my Ring camera on my front door. And it captured a raccoon. We put a box out for delivery drivers. Someone from Amazon or FedEx comes and drops something off, and we'd like to give them, put out snacks for delivery drivers. Unfortunately, this little blighter decided that our snacks are a good free food and has been taking the snacks and leaving the wrappers everywhere. Not a good diet for a raccoon. Even end up putting in a plastic tub with a lid. The raccoon worked out how to do it. So currently our drivers don't get free snacks because of this little one. But this is kind of the problem with just a standard wildlife camera. If it just detects any kind of motion, we will get bears, birds, raccoons, who knows, butterflies, a whole lot of different things. If I was just interested in bears, kind of raised the question of what can I do to just capture information about bears? And so this is where AI comes in. Now, AI is kind of a great way of solving this problem because there's a whole lot of things around vision AI. So vision AI is AI which is designed to work with image data. So it will capture data from a camera, show you, and then process that data and give you information about what you're capturing, whether it's from a still photo or from a video feed. It can give you analytics on what you're doing. It can detect objects in there. It can classify images. It can describe the scene. It can track whether people are wearing hard hats in safety areas. It can track distance in COVID restrictions. It can track stock on shelves. A whole lot of different things we can do with Vision AI. Tim Summers has got an answer about the animals. In Edmonton, Alberta, in Canada, they have rabbits, prairie quail, and coyotes, and sadly thieves. Yeah. I've been quite lucky, but there's been a few places near me that have been broken into. So what we're covering today probably could work as a burglar detector as well. Prairie quail, though, I'm intrigued as to what prairie quail is, because a quail is like a game bird, small bird, quite tasty. But not sure. I've never heard of a prairie quail. And then coyotes. Yeah, don't think we get any of those here. Yeah, these animals you've seen, Tim? I'm curious. Have you actually, obviously rabbits, most people see rabbits, but have you seen coyotes in the wild? I mean, we get bobcats here. I've seen a couple of bobcats around. Haven't seen any mountain lions. We do get those here. Haven't seen those yet, but let's say bear I've seen. So we can use AI. We can train AI models to detect certain things. So there's two different types of vision AI that we can kind of focus on here. There's a whole lot more, but there's kind of two choices we've got for wanting to identify, a bear. Tim says, yes, outside my home office window. So seeing coyotes outside your office. Nice. Yeah, my window, I don't get to see any animals out of my window. I get, Amazon delivery drivers and gardeners. On the other side of my house, I've got a cherry tree, and you can often see raccoons climbing through the tree, eating the cherries out of there. But we don't have a room there that I could sit there and use as an office. It's just kind of in a corridor. Yeah, nice. It's kind of a nice thing to see. So two types of vision AI we can use. So one is image classification, one is object detection. So image classification, you train an image to be one thing or another. So if you ever watched the Silicon Valley show I think it was on HBO, they had hot dog, not hot dog. Same way, you can classify something as one thing or the other, or one thing or nothing. So I could set up image classification for bear or not bear, or I could do bear, raccoon, but that just looks at one image as a whole. Not so good if I've got like multiple bears. It won't say there's two bears. It just says bear. Tim's seen a three-legged coyote with his pack last winter. Nice. It's amazing how many pack-based animal species will look after wounded animals. We have this notion of wolves. It's always the slow ones get left behind, but actually no. The slow ones go up front, the injured ones go up front. So the strong ones behind can keep the pace, and they don't let the injured ones drop behind. So it's amazing how good animals are at looking after the members of their pack that have disabilities. Something that all of us humans could probably learn from. We should treat humans the way that animals treat their pack. That's cool. I'm quite jealous. You need to share some images. That'd be really cool. So image classification, we can do bear, not bear. Not good if you want to count. The other thing is object detection. So object detection, you train the AI model on what something looks like, and it can actually find that in an image. So it can detect multiple instances of an object in an image. And so if we have bears, we can actually use this to count the number of bears in an image. So rather than just saying, that's bear, we can say there's a bear there and a bear there. So we can use object detection to count bears. Which is pretty cool. So what I need to do is get some bear pictures and train an object detection model to count my bears. Now, when we do AI, we have two stages to AI. We train a model, and then we use the model. So when we train the model, what we do is we get pictures. In case of bears, we get a lot of pictures of bears, and we say to an AI model, in this image here, this box here, these are bears. Okay, we'll dive into this a bit more detail in a second. And then once the AI model has learned, we've trained the model, we give it the images, we say learn. Once it's learned, we can then take that model, and then we can do what's called inference, which is where we give that model a new image, and it says, yes, there is the bear, there is the bear. Things like that. So we train the data, and then we actually use the data. We train the model, and then we use the model. Now, a lot of times AI is based off really powerful hardware. So you have GPUs, the things that make Halo and Fortnite look good on your Xbox, also really good for AI, because 3D rendering is just floating point number crunching, and AI is floating point number crunching. So you can use big, powerful GPUs to train models, TPUs, tensor processing units, and NPUs, neural processing units. So the idea is that this AI hardware started off using graphics cards, and we've now got more specific hardware designed for training AI models. So you can use this really powerful AI hardware with your models to train your models and then run your models. It needs to be powerful to train, because training takes a lot of number crunching. So you train with really powerful hardware, and then you might use less powerful hardware to actually do the inference, to run your model. And this is where TinyML comes in. This is where we kind of have this overlap between AI and the Internet of Things through what's called TinyML. So TinyML is all about, you use the power of the cloud to train your AI model, but then what you spit out is a really, really small AI model that can run on a small device, can run on an IoT device or other small bit of hardware. And TinyML is kind of a massive growing field at the moment. It's getting huge. It's very, very popular because people want to run AI on small devices. It reduces the power consumption. You're running on, instead of running on a GPU that runs between 300 to 500 watts of power, you can run it on a microcontroller that pulls milliwatts or macrowatts of power. Your GPU sit there idling, still uses hundreds of watts to idle. Your microcontroller can drop down to nanowatts when it comes to idling. It can save power. So you can run an AI model on a teeny tiny bit of hardware to allow you to kind of save power, just make things faster because you're running it on hardware rather than sending the images to the cloud to run on big, powerful GPUs, and just generally makes things a lot more responsive. Classic example of TinyML, absolute classic example of good use case of TinyML is if you've ever said, okay, Google, or Alexa, or Siri, any of those, you're using a TinyML model. In fact, the AI model that runs on an Android phone to recognize OK Google is 20 kilobytes in size. That is tiny, 20 kilobytes in size, and it uses so little power, your phone can literally be listening continuously to run this AI model to recognize OK Google. This is kind of needed for these kind of smart voice control assistants. You don't want your voice continuously streamed over the internet. It's major, major privacy invasion. It uses far too much power, it uses far too much bandwidth. You want to have your voice recognized on the device. And TinyML allows you to do this. It allows you to recognize OK Google, Alexa, Siri on your device using a small amount of power. So that's kind of some of the power of TinyML. And I can use TinyML with my bear detector to actually detect bears with only very small models running on very low power devices. And what's cool about this, because I can run these small models on my device, I can run them continuously. So if I want to just continuously monitor my camera frame by frame by frame, looking for bears, I can do this by running a TinyML model on a small device. I don't have to continuously stream all the images up the cloud to other models. And if I can run this on a really small microcontroller, I can literally run this on a battery-powered device. So to kind of give you an idea of the types of devices that can run machine learning models, you think about a GPU, kind of traditional big GPU, great big chunky device, runs an AI model. This, however, this is a seed Zhao. Teeny tiny little microcontroller. Only got, I think, 128 kilobytes of RAM in this thing. Not very powerful. It's got an accelerometer. I've actually built machine learning models on here to do fitness detection. So it can work out whether I'm running or rowing based off the movements that I do on this little tiny device. Similar to what you get in like an Apple Watch or a Fitbit, where it recognizes the different motions that you're doing, you're running machine learning models on teeny tiny bits of hardware like this. An image model, I could run a model to recognize bears on a microcontroller like this. Look at that. Size of my thumb. Little camera on there, microcontroller, internet connectivity. Literally, this device could run a bear detector continuously at multiple frames a second, sending results up to the cloud, and draw so little power I could run this off a solar recharge battery. Run it during the day on solar power, run it at night on little rechargeable batteries that are topped up by the solar power. And so TinyML opens up this whole world of running machine learning models on small devices. Carl's Sarganor says, hey everyone, hey Carl, glad to have you here. We're talking AI, tiny machine learning, and you've arrived just at probably the best time to arrive partway through, because I'm actually going to build a bear detector. Talked about some of the theory. A lot of the stuff talked about will make more sense as we dive in and actually build a bear detector. So actually, let's actually build this. Let's try and create a bear detector. Now, I appreciate, obviously, we love animals. We want to care for animals. And I would like to say no bears were harmed in the making of this bear detector. In fact, I'm not even going to use a real bear because I don't want to put a bear in my office next to me. This is the bear I'll be using. I will not be bringing a large, scary animal into my office. So for my safety, I'm using this bear. Polar bears, obviously, one of the most dangerous types of bear. They will literally eat you because they eat everything. Highly endangered animal, needs to be protected, and super duper cute. So we're going to train on a polar bear detector for now, because that's the bear I have. So let's think about the hardware I'm going to use. Now, for the sake of making things run a bit quicker, I'm not going to build this and run this on a microcontroller. Partly to run this on a microcontroller, I would need to code in C++, and the code looks a bit scary. Don't want to be touching that right now for this stream. Just want to show the principles here. So instead, I'm going to go for a Jetson Nano recomputer. So the Jetson Nano recomputer is this little box here. In here. It's from a company called Seed Studios that make really good IoT type hardware. And inside is a Jetson Nano. So Jetson Nano is from NVIDIA, makers of powerful graphics cards and AI accelerated devices. And it's literally a ARM64 based chip with a big GPU on there for running AI workloads. And it's kind of a nice little Linux box I can use for demonstrating this. It's got USB, so I can plug in a USB webcam. In fact, I'll pop it open and show you. Where's the button? There it is. That's it in there. It's a big heatsink, carrier board. So this is the board here. This is the Jetson Nano, GPU and an ARM controller. And then it sits on a big carrier board that's got power and all the USB ports. So that's the Jetson Nano that I'm going to be using. I'd say it's a good, powerful computer, great for demos. Everything I'm doing today, you can run on a small device like this. Just have to get down with some C++ code. I want to stay a bit high level for now, so I'm doing this in Python on the Jetson Nano. Now, software-wise, I'm going to be using software from a company called Edge Impulse. So Edge Impulse, fantastic company. They have got a great tool. It's an online tool for training TinyML models. So you can literally connect it to your device, stream training data from your device, train your model in the cloud, and then output that model to run back on your device. So it's designed to be as easy as possible to train TinyML models. And it's I don't want to say easy because assume you have to have a little bit of knowledge on AI, but it's certainly quite accessible. So everyone can get something going pretty quickly. And they have a whole lot of different AI models you can train using a range of data. So you can use accelerometer data, vibration data, temperature data, kind of any IoT sensor data you can use, including image-based data. And then once I've got my data, once my bear detector detects a bear using the model, I need to see the results somewhere. So I'm using Azure IoT Central just to do a little dashboard so I can see the results of my model. And this is kind of quite a standard pattern. You would train an AI model, run it on a device, on an edge device, so something running that's connected to the cloud but is running on your premises, run those models there, and then send the data up to the cloud to kind of visualize and understand. So let's do it. That's enough talking. Let's actually do it. So in fact, here's the hardware. Here's the, let's get rid of this query here. Here's the seed hardware I'm using. So I'll just drop a link to that in the chat if you're interested. It's quite a nice bit of hardware based on the Jetson Nano. And then I'm going to drop a link into Edge Impulse as well, software we're using. So this is Edge Impulse. It's a fantastic company. You give it raw data. You label the data. So you say, of the data I'm giving you, this is what this data is. You then train AI models against the data, and then it spits out the models, and you can build into whatever you want to work with. And so it's designed to be really quick to do things. You don't have to write any code. And this is kind of the big upside for me because I'm not an AI engineer. I can't write AI code. You give me a Jupyter notebook to build an AI model. Not happening. Can't do it. I don't know my TensorFlows and my Keras, but this allows me to do it. So Janiscu Sims is the cycle of better data. Yeah, actually, this is very important with AI. Is the idea of good data, because you train your model, you give it the data that you think your model needs, and you train the model. But of course, that's trained off data you've created. That's not necessarily real world data, and so you have to have this continuous cycle of retraining your model. So you have to capture data, use that data, and then feed that data back into your model to train it and improve it. So I could train my model on my desk using my bear, but when I put my device out in the real world, it may not function so well. So I need to capture real world bear data and keep retraining my model. So you kind of always have to have this in mind, this cycle, if you need to capture data to retrain your models. Now, when you run AI models in the cloud, normally the data is captured for you. So if I send an image up to the cloud and say, run that AI model, the cloud will keep a copy of that. and I can use that to train my data. If I'm running it on a small device, that image is not kept anywhere. So I would explicitly have to write code to keep the images, store them in the cloud somewhere, so I can use those for training and improving my data. And this opens up a whole world of privacy. So you may have actually seen messages from, the suppliers of voice controlled systems saying, is it okay if we use your data? So like with Apple, for example, with Siri, it'll ask you, can we reuse some of your data for training? Because the idea is it needs more real world data to continuously train the model. So you have to have this cycle of better data, as Janescu 7 says. You've got to keep doing this. You've got to have this way of, you train your model, but you can't assume your model is 100% correct. You've got to be able to keep improving it by capturing data. Yeah, good shout out. So with Edge Impulse, just log in and I can start creating a project. Now, what's cool is they have this developer tier, 20 minutes of job limits for any jobs you run, 4 gigs or 4 hours of data, limited collaboration options, free. So as a developer, I can actually get going for free, which is pretty cool. Now, I'm not going to create a project. I'm going to use one and talk through the steps I do to use the project. But just to save time, I'm not going to completely go from scratch because it can take a while to train these models. So I've got a bear detector. So I've created this project and I've called it bear detector. The first thing I need to do is connect my device and use this to capture data. And data can be a whole lot of different types. I can upload data. I can connect to a range of existing boards. I can connect using my phone, my computer. I can forward data from other devices that aren't supported. I can pull data from the cloud. So kind of loads of different ways I can get data in. But what's cool is if I'm using a fully supported development board, I can literally connect from the board. So I can download firmware that I could put on, ESPI, and then use that firmware to capture data and stream that to Edge Impulse for me. And this allows me to capture the data from the actual device that would be used in the field. And so I can know my data is better. Yeah, if I'm capturing data with a high quality camera and then using that data to train a model that would run on a tiny little camera like this, the data won't be good. Yeah, the model won't be good. I need to train the model based off the real world data. So this allowing me to connect my device allows me to capture that real world data, which is pretty cool. And so let's actually connect my device. Let's connect my device. I'll show you how it works. So I've got a terminal here. I'm just going to go back to my Jetson Nano. So I'm on my Jetson Nano here. The Jetson Nano is a Linux device. It's running a version of Ubuntu, and so I can log in remote and connect to it. And then from here, I can run the Edge Impulse Linux CLI. So Edge Impulse has a CLI I can run, and that allows me to connect my device to the cloud. I just need to add a little option: disable microphone. I don't want to capture the microphone. And this is now connected. So you see, it says here, using camera Logitech webcam C93OE starting, connected to camera. So the CLI that runs on my Jetson Nano will actually look at all the cameras I've got connected and allow me to select the cameras. When I first ran this, I had to log in. I'm not going to run this again from clean now because I don't want you to see my login credentials, but I had to log in. I had to tell it where I was capturing data from, and that was my webcam. So I said, it automatically detected my webcam. I said, capture from that, and it just works. So it's pretty cool. So this device is now connected. I go here and go to devices. My Jetson is connected. Connected to 10:28, which is the time now. Time's 10:29. And then I can start pulling data off my device. And what's cool is you'll see, hello, I'm going to wave here, hello. Actually see a live feed from my camera. So here I am, I'm on the Edge Impulse site, and it's capturing this live feed from my camera. So I can use this to capture the data to train my model. From here, I can choose which device I've got because I have multiple devices connected. I can choose the label I want for my data, and then I can choose which camera if I have multiple. And so I could just put my bear there and capture data. And that uploads a new image. Yeah, maybe move my bear a little bit. Capture another one, maybe move my hand out of the way with the bear. Capture image. And so I'm starting to capture images. And once I've got these images, I can use this to train my data. But I need to label my images to allow me to train it. And so what I do, so I then go to the labeling queue here, and I then have to draw a box around my bear. So here's my box, draw this here, and we'll label that as a bear. So I have to do this. This is how I tell the AI model where the bear is on the image. So if I save that, go to the next image, it's kind of put a box in the same place. I can just go and adjust this box slightly, save that. And this is all part of the training. It's the least interesting part of AI models is labeling your data. Save labels, done, all labeled. So it's the least interesting part. This is where things like Amazon Mechanical Turk or Fiverr, things like that can be quite useful. If you've got a load of stuff to label, you can actually pay people to help you label your data if you need to. Because ideally, for a good model, you need a lot of data. For a basic model, you don't need a huge amount of data. I've got 36 images here that I'm using for my model, which is not a huge amount of data, but this is enough for me to get something that works. Obviously, the more data you have, as long as the data is from a wide varied set, the better it is. If you have a lot of data that's very, very similar, it can be bad because your model gets really good at identifying one thing, not as good at identifying generic things. So once I've got my data, I've got it here, I can then design what Edge Impulse calls an impulse, but this is basically designing the steps for the AI model that I want to build. And so for the first thing I do is actually say I want image data. So I'm building an image-based model. So I choose image data. And here I can actually set the size of the image. Now, if you've not done AI stuff before, what you have with these kind of vision models is what's called a neural network. A neural network has a whole lot of neurons trying to model the way the brain works. But essentially, you have inputs, and each input takes a number that comes in, does some math on the number, and then connects that to another input or another neuron via some kind of connection that also might do some maths. So you have all these kind of input neurons connected to multiple layers of these neurons, and as a number goes in, some maths is done to it, and then as a number gets sent out to another one, maths is done to it. And what the maths is, what's called the weights, is calculated when your AI model is trained. But essentially what it means is you have to have a fixed number of inputs. Your neural network is a certain size, so you have to have a fixed number of inputs coming in, which means your images all have to be the same size. So it doesn't matter what size image you take, it's got to be shrunk down to the same size. Okay, interesting question. Interesting, and I'll take this question. But Beta Sinner says, why are you not using Azure AI? Because Azure doesn't have any TinyML creation tools like this. I can write my own AI code if I want to. So I could use TensorFlow Lite to build TinyML models, but I can't be bothered. This is a nice software as a service platform, so I can just drag and drop and not write any code. Everything I do here, you can do using Azure Machine Learning Studio, but you have to write all the code yourself. With this, I don't have to write the code. But no, it's great question. Great question. I use Edge Impulse because it's easy. I can train the model, can run up my IoT device, and then I can then output this model. And I can use Azure IoT to manage how I interact with my device, manage updates to the model, things like that. But no, Edge Impulse, very cool. It's just a lot easier. I don't have to write any code. We don't. Although, so with Azure Machine Learning, you can have what's called AutoML, where you give it data and it works out what model for you to use. Doesn't work the same way as this. Won't spit out TinyML. There's no way on Azure for me to create a TinyML model. But no, good question. Good question. I work for Microsoft. Here I am in my Azure t-shirt, and I'm showing a third-party tool. But this is a great tool. It's much easier for doing this kind of stuff. Okay, so I need to set my image height so that I have the same number of inputs coming in, and each input that comes into the image is a pixel. And actually, when you think about a pixel on an image, usually that's a color pixel, which means you have 3 inputs, a red input, a green input, and a blue input. So suddenly you have all these neurons for red, green, blue for each pixel that you've got. And that makes the model big. We're thinking about TinyML. We want to make the model smaller. So a lot of stuff is done in grayscale. So the image gets converted to black and white, or grayscale. And so we just have 1 byte per pixel that feeds into our neural network. And actually, you want the images to be quite small because you're looking for generalized things in an image to recognize. The more high resolution images, the better your model gets at recognizing specific things and not so generic. So kind of a classic example would be if you trained an image to recognize ships on lots of high definition pictures of a 3-mast big wooden boat, really high resolution picture of that, it'll be great at recognizing 3-mast high resolution boats. Wooden boats. You give it a single mast small white boat, it may not know what it is. But if you give it things that are just kind of generically boatish shaped because it's low resolution, it gets better at detecting things that are generically boatish shaped. So it kind of work for different boats. So it kind of apply to anything really. You train a model on a specific model of car using high resolution images of that model of car. It's great at recognizing that. But if you do it on a low resolution image, it gets better at recognizing things that are generally car shaped. So low resolution is actually better to a certain point, obviously. So I've got my image data. Image is what I'm processing. And then the model I've got, you choose what's called a learning block for your model. The model I've got for my image is an object detector model. So this is basically saying I want to train an object detector using my images. And so I've got image data, comes in here. We then process the modeling, and then we spit out the feature, which is whether it's a bear or not. So I literally just choose, I start with images and I choose any processing blocks I want to add. If I need to know image processing or data processing, I can add blocks there. And then I choose my machine learning block, the actual model I want to train. And then out comes output. Then from here, I can make any small adjustments. So I can actually look at the images. And once I've got my image, I have to do what's called generate features. And this will actually go through the image and look for what's called features. So it doesn't recognize based on every pixel in the image. What it does, it looks for kind of groups of shapes in the image. It kind of looks for, there's some pixels over here, they've got this shape, and pixels that are this shape. And the combination of this shape and this shape makes this. Kind of oversimplifying it, but a really simplistic example is if you've got young kids, or if you remember when you, back when you were a very young kid, you may have had a shape book. A book that says, here is a rectangle, here is a semicircle, here is a triangle. And then it's got, here is a boat, which is a semicircle on the bottom, and like a rectangle for the mast and a triangle for the sail. Similar kind of idea. You teach it to recognize different features, and then the combinations of these features mean something. So you teach it to recognize a triangle, a rectangle, a semicircle, and those arranged in this order is a boat. Those arranged in another order is not a boat. And so it's kind of this idea of you need to pull out the features from the image. So we train this. This looks for all the features. I can then train my object detection model. And what I'm doing here is a model called FOMO. Okay, not fear of missing out, but faster objects, more objects. So this is the model I'm doing. And I can choose things like training cycles. So how many times does it train the model? And there's various data around how it checks the progress of the model to actually use that. And so I can just start training, and this will go off and start building up my model for me. Now, FOMO is kind of a different type of object detection model to kind of what you're used to. In fact, let me just, for example, urge impulse FOMO. Here we go. So normally with object detection, you do bounding box detection. So if you think about the image I had up here, where are we? You have bounding box detection. So you would say there is the thing here, and this is the box in which that image sits. And so that's kind of the normal object detection, is you get this bounding box. You know, inside the image, this is the part of the image where I get this thing. Now, I really don't care about that. I don't care where the bounding box is. I just care how many bears are in the image. That's all I care about. And kind of that's what FOMO does. The idea of FOMO is based off things called objects with centroids. So rather than put a box around it, it just puts a dot in the center of it. And that the way that it does this allows it to actually be faster. And it says it can track multiple objects in real time with 30 times less processing power and memory than MobileNet or YOLO v5, which are kind of very famous object detection models. And so it's really fast. But what you end up is this kind of idea of the circles around the thing rather than bounding boxes on them. So traditionally, you get like this, you get the box around for the face, whereas FOMO won't give you that. It just uses kind of heat maps to kind of find things and puts dots in there. So it's kind of is much more efficient for finding things. So nice, much quicker, and it's smaller. So it's smaller in terms of the size that spits out. So this is going through, it's training each particular, it's doing what's called epochs. So each epoch is like a training cycle where it improves the training and constantly goes through and tries to improve. So in a few seconds, this will be finished. This will actually give me my model. Finish training. It's now going to tidy up and make everything available. But as you see, I haven't written any code. I've just literally given it the pictures, drawn the boxes, click the button, and it's doing it. So now it's converting TensorFlow Lite Float 32 model. So when you build an AI model, you have these big neural networks, and you store inside the neural network the weights for each neuron, and then what happens between each neuron. So you store a whole lot of numbers for what you multiply numbers by when they come in each neuron, and then what you multiply them by when they go from one neuron to the other, and all this kind of stuff. And normally those stored as float 32s, which are 32-bit floating point numbers, take 4 bytes of memory to store that number. Now, TensorFlow Lite, one thing it can do, it can quantize it to int8. And what that means is instead of using 4 bytes for each number, it uses 1 byte. You lose a little bit of accuracy, but it's a quarter of the size. And these are the kind of tricks that you do with TinyML to make machine learning models that are small. Now, I've downloaded an object detection model trained using Azure Custom Vision. I've downloaded one to go on a phone, and that can be like sort of 60 megabytes in size, which is absolutely enormous. Absolutely perfect on a phone with 128 gigs of RAM. It's really powerful, but not so good on a microcontroller that's only got kilobytes of space. And so this tries to quantize it as small as possible. And so here, for example, the int8 quantized version. So we shrunk our model down. This is a tiny machine learning model. There's a whole lot of techniques that are done to kind of remove parts of the neurons, parts of the connectivity to make it smaller. But this is saying that based off its testing, it's got an F1 score. So how accurate it actually is of 85.7%. So in this case, most of the time it's kind of gets it right. And this peak RAM usage, 243.9 kilobytes. Flash usage, 77.5 kilobytes. So this means I can spit out a model that I can compile down that takes 77 kilobytes in size, uses no more than 250 kilobytes of RAM to run, and runs in 175 milliseconds. And that's just a very, it's a basic estimate, but kind of gives you an idea of how small this is. Object detector on my phone, 60 megabytes. On my device, 77 kilobytes, like 1,000th of the size. So it's made these things very, very small. And then once I've got my model, what can I do? It has the kind of idea of retraining. So if I'm capturing new data, I can retrain my model, just like Janiscu7 said, with the cycle of better data, I can capture and retrain my model. I can do some kind of live classification, actually see it in action, version it to try it out, and then deploy it and put it on different devices. So let's do some live classification, but let's actually do it live from my device. So what I can do is I can go in here, and then I can run, if I run the Edge Impulse Linux runner, this will actually spin up a website running locally on my Jetson Nano that allows me to capture images from the camera and then classify them. So you see it's downloaded the model, it's compiling the model, spitting out some compiler warnings. Doesn't really matter. So what it's doing here is actually taking the model that's been trained, the C++ model, downloading that C++ model, and it's running it live. So if I go back to, if I go to here, I can then connect to my Jetson Nano, and then a bit finicky today. Oh, there we go, bear. It's better last time I did this, so maybe the model needs a bit more retraining. But you see that's picked up a bear. So that's live streaming. And you see it's taking between 3 to 20 milliseconds to run this model. So, oh, there we go. Yeah, maybe some lighting things, but this is going back to that cycle of data. I need to kind of keep retraining. So yeah, So that's got my model trained. My model is now identifying my bear, and it's running in anywhere between 3 to 20 milliseconds. So if you think, if I'm doing this real time, if I'm capturing like 30 frames a second, 30 frames a second means each frame is 33 milliseconds. So I can literally do live object detection at 33 frames a second. Yeah. So not so great today. There was the lighting thing. I need to try and change the lighting a bit and try it again. But yeah, it's kind of not bad. You're going to do any more? Come on. Seems to prefer over this side of the screen for some reason. Oh, it doesn't like my hand on it. There we go. So let's take my hand off. Yeah, there we go. That's what it is. Doesn't like my hand on it. So it's pretty good, isn't it? It's pretty cool. And this is running, say I can easily run this at 30-something frames a second. And I'm just running it on my Jetson Nano because it's kind of easier, but I could then split this out to run on a smaller device. So let's actually look at the Babita Sina asks, why is it black and white? Great question. The reason for doing it in black and white is to make everything smaller. So if we capture a color image, we have 3 bytes per pixel. So every single pixel in the image has to be 3 bytes. The red channel, the green channel, and the blue channel. So that means we need, for every pixel, we need 3 neurons. If we change it to grayscale, then we have 1 byte per pixel. And that uses 1 neuron. So literally in color, the model is going to be 3 times the size. By doing it in grayscale, the model is 1/3 of the size. And the whole point of TinyML is about small. We want to make it as small as possible. And so by using grayscale, that drastically reduces the size of our model. And really, we don't care about color. We're not really interested in color here. The contrast is more than enough for what I needed. Now, if I was trying to identify things in different colors, yeah, if I was doing something to identify, say, money for everywhere that's not the US, where you have different colored notes, you'd probably want the color because that data might be useful to you. But if you're using it in a casino to identify casino chips of different values, again, the color might be of use to you. If I was trying to do different types of fish, the color might be useful to me. For here, the color information is not useful. Optimization of pixel. Yeah, we are trying to optimize the pixel data. Totally. We're trying to because TinyML is about shrinking it. It's every excuse to make the model as small as possible. And by doing it in black and white, we make it 1/3 of the size. So once I've got my live classified image, I can then deploy it. And so from deployment, I can choose how I want to deploy this. So it's designed for IoT devices. So I can spit out a TensorRT library to run on NVIDIA Jetson, raw C++ code, works with any C++ library, an Arduino library. So if I'm using Arduino, I can spit out to that. CubeMX, if I'm using STMicro Cube, WebAssembly, if I want to run it in a browser, which is pretty cool. We've got OpenMV, EthosU, we've not come across Simplicity Studio of Silicon Labs, or I can spit out firmware. So if I just want to get data pushed out to the serial port, I can download firmware for the relevant device. So in this case, I could do the ESPI, which is this little board here. I can spit out firmware for this that runs it and just sends the results to the serial port. So it's kind of up to me. I can either have the source code, I have a binary, or one that works on my computer, which is kind of pretty cool. So spit out any kind of format, and this will spit out a C++ library. So if I want to do, say, a raw C++ library, analyze the optimizations, this will work out how much it uses, and it can tell me the size. So you can say, look, if we do int8, so the quantized version, 77.5 kilobytes of flash. If you go to the float 32, slightly bigger amount of flash, more memory usage, just the way it kind of compress the image down. That's pretty cool. And they have this thing called an Eon compiler as well, which can really reduce your sizes if you want to. So once I've got this, I want to then use this in my application. And I'm running Python because that's how I roll. And so what I want to do is I want to actually run a Python app on my device to capture information about my bear. So I'm just going to stop the webcam, the the website running just so I can build this. And I have got some code here to actually do this and connect up to the cloud. So I'm running on my Jetson Nano. This is Visual Studio Remote SSH. So with Visual Studio Code, what I can do is I can remotely connect to any device that supports SSH. So from here, I can remotely connect to my Jetson Nano, and everything I do inside Visual Studio Code is as if I'm running on my Jetson Nano. The terminals for Nano, I edit files on the Nano. If I debug, it runs the Nano. Everything runs if I'm on the Nano. I'm on my Mac, just remotely connected, SSHing into my Jetson Nano, which is pretty cool. Then from here, I can then download the actually download my model. So I got Edge, Impulse, Linux runner. What is my download? And then model file.eim. And this will download an Edge Impulse model file. And I can then, I've already downloaded it, so it's not even going to download it again, which is quite nice. Yeah, let's just rename this one. Model file 2. There we go. Yeah, no, you don't open you. So let's. No. It likes it. It likes what I've got. Okay. But this basically downloads a Python model. So take what we here and download it as it's a raw model file format that I can then use from the Python SDK, C++ SDK. So this is finished. It's finished with the analytics. You can see here's the analytics. So the Float 32 is faster, uses a lot more memory. It's quite cool. Carl Sarganar asked a great question. Will this demo also run on a hardware like a Raspberry Pi 4? I don't think it has any hardware specifically for AI that's there, so I'm not sure. This will totally run on a Raspberry Pi 4. I just chose the Jetson Nano because I think it's a cool bit of hardware. I'm not really using any optimizations for the GPU. So this will totally run on a Raspberry Pi 4. In fact, when I do my, when I connect to device, it supports Raspberry Pis. So if I actually look at the dev boards that it supports, show you here, I could literally take a Raspberry Pi. Where are we? Linux boards, Raspberry Pi 4. There you go. So it works with it works with USB webcams, also works with the Raspberry Pi camera module. And I can plug that into the Jetson Nano, or I can plug that into Raspberry Pi and it will work on there, which is really nice. I actually did I tried out on the Raspberry Pi, and the streams, the speed is basically the same. It's kind of between 9 to 20 milliseconds to process each image, which is pretty cool. So it works beautifully on the Raspberry Pi. I'm just using the Jetson Nano because I've got one and I can. Now, rather than you run the C++ code and compile that, the model here I've got, this is their format. EIM is the Edge Impulse model format. It's kind of like a TensorFlow model you get as a PB and labels. It's Edge Impulse's format. And they have SDKs for you to use this. So I can use this from C++, I can use it from Python and other languages. C++, normally you get source code with the model actually hard-coded in there as hex data that compiles down to make it more efficient rather than having to load a file. But I've got this, my classify code here. So I import from Edge Impulse Linux image, import image impulse runner. So I can use this to run the image. And then in my code, what I do is I load up my model and then run this, initialize my runner, and then the runner actually connects to the camera. So I don't even need to write the camera code myself. The runner connects to the camera. So the runner will pull images from camera 0, which is my webcam, my first camera. Then take the image, process it for the features, so kind of pull out all the shapes that it recognizes, and also pull out a cropped image, because webcams pull out rectangular images. Everything's with AI is usually square. So I choose whether on the left, right, or center. In this case, I want the center of the image. So that will then process the center of the image, and then it'll classify it. So actually run it through the object detector. So do the inference. Once I've done that, I'm actually writing out the image that was captured. And then if there's any bounding boxes, so their object detection API still works on bounding boxes because they have classic object detection that does bounding boxes. But with FOMO, bounding boxes, tiny little dot in the middle. So I can use it to get the center point. And if I have one, I actually draw a circle on the image. And then I track the bears. And then I've just got some logic that says only track a bear as a new bear. A bear hasn't been seen for the last 5 seconds. If track again, it's a new bear. Real world deployment would be a bit longer. Yeah. If I capture a bear, doesn't matter if it goes in and out of frame, I'll count it as one bear until I spend maybe 10 minutes without a bear. And that's it. Well, that's how I run the model. And then I send the data up to Azure IoT Central. Just got a bit of code here to connect to Azure IoT Central. So what that means is if I actually run this, F3 UI, let's take the model. You see it's now detected a bear. If I actually look at the image, you see there's the bear and there's the circle. If I take the bear away, wait a few seconds, bear, no bear detected. You see it's update the image, bear, put the bear back, bear detected. Hasn't updated with the circle. Yeah, so I'm going to use this to kind of debug it, and that sends data up to the cloud. And if I go back here, go to my so I've got an Azure IoT Central dashboard up here. So Sargonaut asks, what is it sending to Azure IoT? Just identified bear data for dashboards? Yes. So literally what I'm sending, I'll show you in fact. So if I go to my raw data, I'm literally sending a Boolean flag, bear detected, true or false. That's all I'm sending right now. So I could do count of bear, I could do other things. Right now, I'm just sending true or false to say whether there's a bear that's being detected or not. That's the only data I'm sending. And then from there, what I can do, I've got a dashboard here that shows, just showing state history, bear detected, true, false, true, false. I can look at the history when bears were detected. There's so many other ways I can slice and dice the data. I just want to go for a simple true or false, just tells me whether it's detected or not. So in the real world, I would look at this and say, oh, a bear was detected at this particular time. But I just wanted something a bit more simplistic. So yeah, so if you've not come across Azure IoT Central before, it's a software as a service platform for IoT devices. So rather than you having to build all your dashboards and management, this does all that for you. If you use Azure IoT Hub, that's the underlying technology of this, which is a pipe that IoT data gets sent to, but this puts a whole set of management tools on top. So you can do things like define device templates, which defines what data you're expecting. So in this case, I'm expecting a telemetry field called bear underscore detected that is a state field that's a string of true or false that has a Boolean value. It's kind of like an enum value. So that's what I'm expecting. And I can then define, this is the view that I want to see. This is kind of the dashboard I want to see. Kind of drag and drop different dashboards on here. So I'm going to find a whole lot of stuff. I can do commands, which instructions you send to the device to do things, I can do data from the device, properties that get synced to the device, manage all that, build cool dashboards for it. And then I can launch a whole data explorer to analyze my data over time. I can build a whole lot of different types of custom dashboards for multiple devices instead of individual devices. I can set up jobs to run commands on the devices to update the firmware. I can set up rules. So if a bear is detected, it sends me an email. Do that now. So I could say, right, my device template is this. If all the conditions are true, bear detected equals true. That's my condition. Bear detected equals true, and I can add an email action to it to send me an email. So which is pretty cool. So don't need to worry too much about writing in this myself. Azure IoT Central does all this kind of stuff for me. And it's got hooks in there as well where I can export data to other systems and manage that and set up security and all this cool stuff. It's great software as a service platform. But yeah, for now, I can use this to see from this particular device, there's my bear information. Stay Blazing says, that's cool. First time I've learned a little about how this stuff works. Glad you enjoyed it. Yeah. This is basically my bear detector. This is my bear detector end to end. So Stay Blazing, I'm glad you enjoyed it. But yeah, this is it. This is my bear detector. I'm going to grab a link for you all if you want to see the code. I haven't written this up yet properly. I've been a bit slack on this one. Can't type today. I really can't type today. I've just dropped this in the chat. If anyone actually knows around the code, I haven't put a full blog post of how to do it. This video is the blog post of how to do it, but that's the code they want to see. But yeah, so Stay Blazing says, when linked with doing something you enjoy, seems like the way to learn. Oh, totally. Best way to learn something is to think of something fun and build it. Yeah, if you want to learn IoT, there's so many fun projects you can do, from bear detectors to soil moisture detecting to so many cool stuff. Lots of cool things you can do. So glad you enjoyed it. But yeah, that's my bear detector. Thank you very much for joining me. Carl Sarganau's awesome demo. Thanks for this. Check out the code and try on a Pi sometime. Definitely works on a Pi. Nice to do it. Baldy, I guess, says, how would you retrain the model and redeploy it? Great question. What I would need to do is either retrain it manually or write something on my Jetson to capture data for me to allow me to retrain it using data from the device. And then I would probably update firmware. If I could use IoT Edge, which allows me to kind of manage pushing pushing new models to the device, or I could, if I'm running it in C++, I can actually push the firmware out. So kind of a lot of ways to do this. So yeah, Little Andy 77 says, thanks, that was nice, bye-bye. Tim Summers enjoyed it. Yeah, thank you very much. Really enjoyed having you here. This was a really good session, so thank you for joining me.
Thank you, everyone, and thank you to our speaker. Oh, were you going to say something, Jim?
No. Oh, good. Go ahead.
Oh, okay. Sorry. Thank you, everyone, for joining. Thank you to our speaker. If you have any feedback, we'd love to hear what you have to say. Please visit the link on the screen or in the survey for the specific event. It's 16659. Down below, if you have been joining us this past month every Friday for Jim's IoT for Beginners, he does have one final session this Friday with lesson 4. I've added the link on the screen and you can find it in the chat. He also does have a session tomorrow, and I've added that session in the chat as well. Thank you, everyone. Until next time. Bye.
Cool. Thanks. Bye.